Everyone is obsessed with the artificial intelligence revolution. We are constantly talking about how AI will take our jobs, write our code, and maybe even achieve consciousness. But we are completely ignoring the massive physical elephant in the room. The plug. Here is the terrifying math that nobody is talking about. According to the International Energy Agency, a standard Google search uses about 0.3 watt-hours of electricity, but a single prompt to ChatGPT, that burns through 2.9 watt-hours, almost a 10 times increase. Overnight, the AI boom has completely shattered our global energy projections. We are building digital brains that are starving for physical power. So the mainstream narrative tells you the solution is simple, right? Just build more solar panels, build more wind turbines, and store that green energy in massive lithium batteries. We are told the future of the planet depends on who can dig up the most lithium. But that is a $1 trillion illusion. The reality? Even with the massive investments in grid-scale battery parks worldwide, the International Energy Agency reports that all global battery storage combined can handle less than 1% of the planet's daily electricity consumption. Less than 1%. Batteries don't light up the night. They barely smooth out momentary grid hiccups. The idea that we can store our way out of this energy crisis is mathematically impossible. We don't have an energy generation problem. We have a storage and geography problem. We are tethered to the ground, trying to catch sunlight through a thick atmosphere, half of the time in total darkness. But what if we just bypass the geography entirely? Welcome to the ultimate infrastructure leap, space-based solar power. For decades, this sounded like absolute science fiction, but the physics are surprisingly elegant. And more importantly, the system is already working. Here is how the mechanics actually work. When you put a solar panel on Earth, it's crippled by the atmosphere, by clouds, and by the 12-hour night cycle. But if you place a solar farm in geostationary orbit, roughly 36,000 kilometers above the equator, it sits in perpetual sunlight. According to the European Space Agency, an orbital panel doesn't experience night. It doesn't experience weather. It produces a continuous, uninterrupted flow of electricity, what engineers call baseload power. Because of this, an orbital panel generates 8 to 10 times more energy per year than the exact same panel sitting on Earth. But the obvious question is, how do you get a gigawatt of electricity down to Earth without a 36,000 kilometer copper wire? You don't use wires, you use microwaves. You convert the solar energy into high-frequency microwaves and beam them directly to a specific target on the ground. The target is a massive field of antennas called a rectenna, which catches the invisible beam and instantly converts it back into electricity to feed the grid. And this isn't just theoretical math anymore. In January 2023, Caltech launched the Maple demonstrator into orbit. For the first time in human history, they successfully beamed a detectable power signal from space directly to their lab in Pasadena. They proved the physics. The European Space Agency knows exactly where this is heading. That's why they've officially launched the Solaris Initiative, actively funding the groundwork to put gigawatt-scale commercial power stations in orbit by the 2030s. The blueprint is real. The physics are proven. But here's where the story shifts from engineering to absolute global dominance. If you can beam electricity from space, you are no longer just an energy company. You are a geopolitical superpower. Historically, global power was dictated by geography. Who had the oil wells? Who controlled the pipelines? Who guarded the shipping lanes? But space-based solar power completely decouples energy from geography. Why is this happening now? Because of the launch costs. During the space shuttle era, it cost around $54,000 to send a single kilogram of payload into orbit. Building a massive power plant in space was economic suicide. But today, thanks to next-generation reusable rockets like SpaceX's Starship, Citigroup projects that launch costs will plummet to under $100 per kilogram. A 99% collapse in logistics costs. That cost collapse turns an engineering pipe dream into the most lucrative monopoly of the 21st century. The new petrostates won't be countries in the Middle East. They will be the tech and aerospace giants who own the orbital infrastructure. And the military implications? They are staggering. The U.S. Naval Research Laboratory is already heavily invested in microwave power beaming for a very specific reason: the death toll of logistics. Historically, a massive percentage of military casualties in conflict zones happen during attacks on fuel and diesel convoys, what the military calls tethered supply lines. Imagine a future where an advanced military base or disaster relief camp doesn't need a vulnerable convoy of diesel trucks to keep its radars and hospitals running. They just drop a rectenna on the ground, send a coordinate to an orbital station, and instantly receive a gigawatt of power from the sky. But here is the rational risk we must face. When energy becomes a wireless transmission, whoever controls the switch in orbit controls the world below. A system this centralized is a prime target. The cyber wars of tomorrow won't just be about stealing data. They will be about hacking the beam. We are leaving the age of extraction and entering the age of transmission. For centuries, energy was a physical resource we violently dug out of the dirt. Tomorrow, it will be a software that we download from the sky.